Ever splashed gasoline on your hand at the pump? Remember that quick, almost startling chill? It's a strange thing, isn't it? We expect liquids to be, well, liquidy wet maybe, but not necessarily cold, yet certain liquids like gasoline and perfume have this knack for sending a shiver down our spine. They feel much colder than they should, like an ice cube briefly grazing your skin. This intriguing phenomenon isn't just a quirk of these specific liquids, it's a fundamental principle of science at play, a dance between molecules, heat, and our own perception. It's a reminder that the world is full of these little mysteries waiting for us to unravel them. So, buckle up as we delve into the fascinating science behind why some liquids feel surprisingly cold. We'll explore how these liquids pull off their disappearing act, transforming from calm puddles to invisible vapors. We'll discover how this vanishing act is the key to their chilling touch. And we'll even uncover how our own brains play a part in amplifying this sensation. Get ready to see everyday liquids in a whole new light, appreciating the hidden wonders behind their coolness. It's a journey into the unexpected where a simple splash can reveal the elegant laws governing our universe. The secret to the chilling touch of liquids like gasoline and perfume lies in a process we often take for granted: evaporation. It's the same phenomenon that dries our clothes on a sunny day or transforms a puddle into thin air. But what exactly is evaporation? And how does it make things feel cold? Imagine a bustling city street filled with people moving about. Evaporation is a bit like that, but instead of people we have molecules, the tiny building blocks of everything around us. In a liquid, these molecules are constantly jostling and bumping into each other, like a crowded dance floor. Some molecules, full of energy and raring to go, manage to break free from this molecular mosh pit. They escape from the liquid's surface and zoom off into the air, becoming a gas. This is evaporation, the transformation of a liquid into a gas at its surface. But here's the catch: not all molecules are created equal. Some are more energetic than others, like those eager dancers pushing their way to the front. These high-energy molecules are the ones most likely to break free and evaporate. And this is where the cooling effect comes into play. As those energetic molecules make their grand escape during evaporation, they don't leave empty-handed. They carry away some of the liquid's heat energy with them, like runners grabbing a quick drink at a water station. This heat transfer is the reason why evaporation leads to cooling. Think of a pot of simmering water. As the water heats up, the molecules get more and more energetic, bouncing around like popcorn in a hot pan. Eventually, some of these highly energized molecules near the surface will have enough oomph to break free and become water vapor, taking some heat energy along for the ride. This is why we see steam rising from the pot. It's those escaped water molecules now floating freely in the air. And if you've ever held your hand above a steaming pot, you've felt this cooling effect firsthand. Now imagine this process happening at a much faster rate, with molecules escaping into the air at lightning speed. That's precisely what happens with liquids like gasoline and perfume. Their molecular structure allows for rapid evaporation, making them feel significantly colder than, say, water. Not all liquids are created equal when it comes to evaporation. Some, like gasoline and perfume, are eager to break free and become a gas. Others, like water or honey, are a bit more clingy, preferring to stick together as a liquid. This difference in evaporation rates boils down to the forces holding the molecules together. Imagine a group of friends holding hands. Some friends might have a loose grip, easily letting go if they need to move around. Others might hold on tight, making it harder to separate them. Molecules in a liquid behave similarly. Liquids with weak intermolecular forces like gasoline are like those friends with a loose grip. Their molecules don't cling to each other very strongly, allowing them to easily break free and evaporate. On the other hand, liquids with strong intermolecular forces like water are like those friends holding on tight. Their molecules require more energy to overcome these forces and escape into the air. This explains why a puddle of gasoline evaporates much faster than a puddle of water on a warm day. The gasoline molecules are quicker to break free and become a gas, while the water molecules prefer to stick together, taking their sweet time to evaporate. Section 5. Body heat on the line. How evaporation cools us down. Now that we understand how evaporation works and why some liquids excel at it, let's connect it back to our skin and the sensation of coldness. When a liquid like gasoline or perfume comes into contact with our skin, it's like a thirsty traveler finding an oasis in the desert. Our bodies are naturally warm, radiating heat like little furnaces. This heat energy is a gold mine for those eager to evaporate molecules in the liquid. They quickly absorb this heat, using it as fuel to break free from their liquid bonds and zoom off into the air as a gas. As these molecules make their escape, they take some of our body heat with them, leaving the skin feeling cooler. It's like a miniature air conditioner effect, with the evaporating liquid drawing heat away from our bodies. The faster the evaporation rate, the more pronounced this cooling sensation becomes. This is why a splash of gasoline feels noticeably colder than a splash of water. The gasoline evaporates much faster, quickly drawing heat away from our skin and leaving us with that characteristic chill. Water, on the other hand, evaporates more slowly, resulting in a less dramatic cooling effect. Section 6. A matter of degrees. Why some liquids feel colder than others. The intensity of the cooling sensation we experience depends on several factors, all intertwined in a delicate dance of physics and chemistry. One crucial factor is the liquid's vapor pressure, a measure of how readily it evaporates. Imagine a pressure cooker, steam building up inside, pushing against the lid. Vapor pressure is similar. It's the pressure exerted by a liquid's vapor when it's in equilibrium with its liquid phase. Liquids with high vapor pressure, like gasoline and perfume, are like those eager beavers in the molecular world, constantly trying to escape into the air. These high vapor pressure liquids have a larger number of molecules escaping into the gaseous state, leading to faster evaporation rates. And as we've learned, faster evaporation means a more pronounced cooling sensation on our skin. Another factor influencing the perceived coldness is the liquid's thermal conductivity, how efficiently it transfers heat. Liquids like metals are excellent conductors, quickly transferring heat away from our skin. Others like wood or plastic are poor conductors, acting as insulators. Section 7. Tricks of the mind, how our brain plays a role in feeling cold. While the science behind evaporative cooling is fascinating, it's only part of the story. Our perception of coldness isn't solely determined by physics and chemistry. Our brain, the ultimate interpreter of sensory information, plays a significant role in shaping our experience. Think about it. We've all experienced the placebo effect, where our beliefs and expectations can influence how we feel. The same principle applies to our perception of temperature. If we anticipate something to be cold, our brain might amplify those sensations, making us feel colder than we would otherwise. This is where the power of association comes in. We associate certain liquids like gasoline and rubbing alcohol with being cold. This association stems from our past experiences, the quick chill of gasoline at the pump, the cool sensation of rubbing alcohol on a wound. These memories create a mental shortcut, priming our brain to expect coldness when we encounter these liquids again. So, when we touch gasoline, our brain, already expecting a chilling sensation, might amplify the signals it receives from our skin, making the experience feel even colder. More than meets the eye, the psychology of cold sensations. This interplay between physical sensations and psychological factors highlights the subjective nature of our perception. What feels cold to one person might feel only slightly cool to another. Our individual sensitivity, past experiences, and even our emotional state can all influence how we perceive temperature. For example, someone who's particularly sensitive to cold might experience a more dramatic chill from gasoline than someone who's generally less sensitive. Similarly, our emotional state can play a role. If we're already feeling anxious or stressed, our body's response to cold sensations might be heightened, making the experience more intense. The key takeaway here is that our perception of coldness is a complex interplay of factors, both physical and psychological. It's not just about the liquid's properties, but also about our individual experiences, expectations, and how our brain interprets those sensations. It's a reminder that our experience of the world is shaped by a fascinating interplay of factors, both within us and around us. Everyday Wonders unveiling the cool secrets of familiar liquids. The chilling touch of gasoline and perfume isn't just a scientific curiosity, it's a phenomenon we encounter in countless everyday experiences. Take, for instance, the refreshing coolness of rubbing alcohol on a scrape or the invigorating chill of a menthol cough drop. Rubbing alcohol, like gasoline, evaporates quickly, drawing heat away from the skin and creating a cooling sensation. This is why it's often used to bring down fevers or soothe sore muscles. The rapid evaporation helps dissipate heat from the body, providing temporary relief. Menthol, The compound responsible for the cooling sensation in cough drops and muscle rubs works in a slightly different way. It doesn't actually lower the temperature but rather activates cold-sensitive receptors in our skin, tricking our brain into perceiving coldness. These examples highlight how the principles of evaporative cooling and sensory perception extend beyond the realm of gasoline and perfume, influencing our experience of seemingly ordinary liquids. It's a reminder that science is all around us, even in the most mundane aspects of our lives. From gasoline to perfume, a common thread of coolness. As we've explored, the chilling touch of liquids like gasoline and perfume is a fascinating interplay of science and perception. Rapid evaporation, driven by molecular properties and influenced by factors like temperature and humidity, sets the stage for this cooling effect. Liquids with weak intermolecular forces like gasoline evaporate more readily, quickly drawing heat away from our skin. This heat transfer, coupled with our brain's interpretation of these sensations, creates the perception of coldness. Our past experiences, expectations, and individual sensitivity further shape this experience, making it subjective and nuanced. The next time you encounter the unexpected chill of gasoline or the refreshing coolness of a menthol cough drop, take a moment to appreciate the intricate dance of molecules, heat transfer, and sensory perception at play. It's a reminder that the world is full of hidden wonders, waiting to be discovered in the most ordinary of places. The science of chills, unraveling the mystery of cold liquids. So there you have it. The mystery of why some liquids feel cold unraveled. It's not magic, but the elegant workings of evaporation, heat transfer, and our brain's interpretation of sensory information. The next time you pump gasoline or spritz on perfume, you'll have a newfound appreciation for the science behind that fleeting chill. It's a reminder that the world is full of these little mysteries waiting for us to explore and understand. From the intricate dance of molecules to the subjective nature of our perception, there's always something new to discover. So keep asking questions, stay curious, and never stop exploring the wonders of the world around us.